Okay, so continue. So today I'm going to talk about stochastic second-order methods for deep learning. So this work is based on the collaboration with -14 at Huawei. There are a couple of students. For example, Minghan Yang is my PhD student. Xudong is a master student, and Hongyu is an undergraduate student. So first, let me just briefly talk about why deep learning is difficult. So a typical deep learning problem can be written as a minimization of the summation of functions. For example, psi I is our function, where psi is our loss function. For example, can be quadratic square or cross entropy, depends on your particular data sets. And the xi and yi are given data, where yi is the neighbor of xi. So this here h is the output of the network. We will explain it later. So the objective function can be highly non-convex or even non-smooth. For example, because of some non-smooth functions in the neural networks. I guess one of the main difficulties is the case of dimensionality in two senses. One is the number of data samples. The capital N can be huge. For example, in ImageNet, right? So the number of images can be easily up to 1 million or more, right? And then the dimension of the variables can be huge. I will explain later. For example, in WesNet, the architecture can be in this form, right? So the number of parameters of WesNet 50 and the ImageNet 1K can have easily have 25 million variables. Therefore, given those huge number of parameters, so the dimension of theta can be 25 million. Therefore, many things can be difficult. I will explain to you later. Another thing is, for example, recently the natural language processing, the model complexity is increased very faster. For example, even a few years ago, the number of parameters is 94 million, which is larger than the WesNet. But last year in May, we have so-called GPT-3. It has 175 billion. The number of variables is this kind of huge. So then the training cost can be very expensive. So training this GPT-3 can be at least $12 million US. So I think this is not possible at most of the places. Only large companies as OpenAI or Google, those companies can afford to train big neural networks. So this is one difficult, right? So the dimension is huge, but in terms of operation, we have a few other difficulties. So they can be interpreted in this figure. We have, suppose we are going to minimize solve this expectation. The parameters lives in a certain functional space, in a certain space. Suppose if the space is large enough, we assume we can have a ground truth, right? Then we approximate this function space by, for example, by using neural networks. Of course, the H is our neural network, and the theta is our parameters. So in this way, the first difficulty is the approximation area, right? Because we are using a smaller function space to approximate a larger one. Another thing is, if when we train the neural network, we only do it on a finite number of examples. So here is expectation. But what we can do is we only do in a finite number of examples. Then this is so-called generalization. Right? And we are going to solve this problem by use any of your favorite algorithm, for example, SGD or Eiden or other algorithm or the second order methods in this talk. Then this is another difficulty. So in practice, when you train a neural network, you usually encounter a difficulty, for example, to reduce 1% or 0.5% of testing accuracy. Then you will take a lot of epochs, a lot of iterations to achieve the scale. But so the reason is we split our data into the training data and the testing data, right? And what you are doing, the operation is on the training data, but measure the accuracy on the testing data. Right? So this kind of challenge we never face in doing ordinary optimization problems. So I guess those are two major difficulties. But today I'm mainly focused on the first one, how to solve the dimensionality challenges. So let's look at a simple case, a feedforward network. For example, so the input is a vector or matrix. It's okay, and the output is a certain vector, and it is obtained in this way. So AI is our, for example, is the input. The W is the matrices. This is our parameters, right? And after this matrix vector multiplication, then we go through certain kind of iteration name. For example, this can be a value function, right? And we repeat this process for several days. So this is a very simple case. And what is our parameters? Theta is a vectorization of all those parameters. Of course, for simplicity, we ignore the base term. Then let's look at what is the gradient. The gradient simply for the back propagation can be written as a one-to-one matrices. Because if you see the W is a matrix, right, and this is a derivative of the loss function with respect to this parameter, this matrix WL. The dimension is the same, right? This is GI is GL is this way, and AI is computed in this way. We're going to take advantage of this kind of structure, but in stochastic gradient, we simply use a gradient in this way. Even if you take a look at the convolutional relay, the gradient can also be expressed as a multiplication of two matrices. So let's try to understand the loss function in statistics. So let's Q be the true data distribution. Q height is the training distribution given the sample days. And the P is the named distribution, right? And then what is our loss function? It can be interpreted as a minimization of the Q divergence between Q height and the P. Right? So where the Q divergence is defined in this way. And then if we do the calculation, it can be expressed in this way. It actually is a summation of the log probability of certain functions. So right now, let's go back. So before I go into the detail, let's review what is a critical product. So the critical product between two matrices A and B is defined in this way. So this is Aij, this is each element times B. This is a huge matrix. So suppose we have a matrix whose dimension is more than 1 million. Suppose if we want to compute its inverse, then the computational cost can be very expensive, right? However, if the matrix can be written as a canonical product between A and B, then the size of A and B can be only a few thousand. And then we have this relationship. So the inverse of this matrix can be written as the inverse of A canonical product between B inverse. Therefore, we can afford to compute the inverse of whose size can be more than 1 million. We can do this. So this is the core idea of the so-called KFAC method. So let's look at, let's go into the detail. So what is the Hessian matrix? The Hessian matrix is the expectation of a 1-to-1 matrix, where psi is our loss function. So let's try to compute this in detail. So in practice, we only have sub-sample data, right? We only have empirical Hessian matrix. So remember, our gradient can be written as this way. So it's vectorization because theta is a vectorization of W. So for this one, we have vectorization for this matrix to a vector, but this is a 1-to-1 matrix. And then we use this kind of structure, this, right? So we have A cross B and C cross D equal to A times C and cross B times D. So if we plug into this relationship, we can see for this simple neural network, the Hessian matrix, empirical Hessian matrix can be written in this way. So expectation of 1-to-1 matrix cross canonical product between another 1-to-1 matrix. Right. This is very important observation. We'll use this fact. On the other hand, we can also compute the Hessian matrix. The Hessian matrix is from the understanding of statistics. From the observation, we compute the Hessian. So the Hessian can be written in this form. It's a summation of two parts. If you know that, if you take a look at the loss function, essentially it's a generalized nonlinear least square problem. So we know that for the Hessian have two parts. One is a Gauss-Newton matrix, another one is a Hessian of the nonlinear functions. So similarly, we have same structures. So this part is corresponding to the Gauss-Newton matrix. So let's take a look. So this matrix is very similar to this Hessian matrix. The only difference is this part. So it's so actually they are, in certain cases they are equivalent. And so it's a capital GI. So we're going to take advantage of those structures. So as I explained, if we just use the gradient method, we are never going to use the Hessian matrix and the Hessian matrix. But if we are going to use if we're going to have a second order type method, we have to consider the second order derivatives. So there's so-called natural gradient method in statistics and machine learning. So this method is very simple. We compute the so-called natural gradient direction. So this F is the Hessian matrix. We take the inverse of this matrix times the gradient. So because we have to take an inverse of certain matrix, it can be called a second order type method. But this method is related to the steepest descent direction in this sense. So we minimize this function. Right? The D is in a small neighborhood defined by this scale divergence. So if this epsilon goes to 0, then this direction, this minimized D, is defined by the Hessian matrix, by the natural gradient direction. Therefore, it can be understood as a gradient method. However, the main difficulty is how we compute its inverse. So this so-called KFAC method is we're trying to find a canonical factor approximation to this Hessian matrix. of course, we take a block the diagonal approximation to it. We omit all we delete all the off diagonal parts, only keep the diagonal part. Then we take a look at the Hessian matrix. And as I explained, even for the convolutional relay, the gradient is a vectorization of these matrices, which can be written in this way. And then we plug in the formulation, right? Then we have this relationship. So this part is a vectorization of identity matrices. So most of them are 0, right? Because only for example, dimension is n, we have only n elements are 1, or other elements are 0. However, we can approximate it by identity matrices, and then we can have this very beautiful relationship. And once again, we can have this one. So it's an expectation of a clinical product between two matrices. However, it's still difficult to compute its inverse because we have many. It's a summation of them, right? So the K observation is suppose A and G are independent. Then we can first take the expectation, then compute the clinical product. Therefore, it can be written as a clinical product between two matrices. So that's the most important observation by Martens and Groos. So therefore, right? So they take the matrix in this way. Of course, to ensure the matrix is invertible, we add a small scalar has identity, and then we take the inverse by use the property of a clinical product. We can easily compute the inverse this way. So this is the KFAC method. So today I'm going to show you two other methods to take advantage of the structure of the Hessian matrices. The first one is quasi-Newton type method. So once again, let's look at the Hessian, right? We know the Hessian can be written as a summation of two terms. So one term is relatively easy to compute, and another term can be very expensive because in this part we only need to compute the second order derivatives. The first one, we only need to compute essentially the gradient, right? Like the Jacobi matrix, Gauss-Newton matrix. Then we take a look at a few cases. So auto is H and Nanta. So for example, for certain simple functions, if your data set is small, if your neural network is simple, then we can afford to compute the Hessian at a few dampers. Then you can construct H in this way. Then if you treat the problem as a generalized nonlinear least square problem, just plug into the formulation, the H can be in this way. But so if you compute the sense in this way, then in most of the implementation of neural networks is not affordable. For example, if you compute the Hessian in this way, in PyTorch or TensorFlow, this can be very expensive because of the structure of the. However, I've already explained to you the Hessian structure in this page, right? So it's a summation of those two things. Of course, then, for example, this term is very similar to the KFAC matrix, right? Then we can approximate this part by the KFAC matrix. And then we can approximate this part by, for example, by quasi-Newton matrices. So this is our idea. So it's very similar to the quasi-Newton method for nonlinear least square problem. Essentially the same type of method. So our method is as follows. So we construct the approximation BK to the Hessian, and then we compute the direction. Of course, we have to update the parameter Nanta in a certain way, and compute the DK, right? So the most important part is how we compute this direction. So let's look in detail. So because our BK has structure, we have a simple HK and we approximate lambda k by quasi-Newton matrix. For example, we can approximate lambda by the limited BFGS method. So if you know this BFGS method, it can be written as a no-rank update. So limited memory has constructed a no-rank update to the Hessian matrix or inverse of the Hessian matrices. So suppose the inverse of H is simple, it's possible. Then because this part is a no rank, then you can use the so-called SMW formula to compute the inverse explicitly in this way. But this based on, so inverse of this matrix is simple. So let's look at another case. Suppose HK itself is a no-rank matrix. So there are a few cases. For example, HK is constructed from the empirical Fisher matrices. We know the Fisher matrix is a summation of one-to-one matrices, right? But usually we can only afford to compute it a few examples. For example, the batch size is only 64 or 128. Then this is no rank matrix comparing to the dimension of the parameters. Or we can also construct a no rank matrix by using the so-called Nastron approximation. Suppose W is the original matrix. It itself can be expensive, but you can still afford to compute a matrix modification at once. And then suppose omega itself is a random matrix, it's no rank, then ZK is no rank, the H can be, this matrix is no rank. Once again, we plug into the expression of lambda by L BFGS because this is no rank. And the HK itself is no rank. Again, you can use the SMW formula, right? You can compute the inverse directly. So this is our method. So now let's look at the convolutional relay, because the convolutional relay is kind of complicated. But by doing some assumptions and by some calculation, we can show that the Hessian in this case is actually a conical product between two matrices. So the assumption is very similar to those used in KFAC method. Then suppose the diagonal part, block diagonal part of the Hessian has this form, the conical product between two matrices. Then we can construct an approximation BK in this way. So either we approximate the four matrices by adding some matrix lambda k, or we approximate this GK in this form. Right? Because why we can do this way? Because in practice we only can afford to compute those matrices on a few examples, right? So even though this is explicitly this is only holds in exploitation, but under a few examples we can do those two kinds of approximation. Then we have two kinds of quasi-Newton condition. Right? So UK is the difference of parameters, and V is the difference of the gradients. Of course, H is the stochastic gradients. Then we plug into the quasi-Newton condition. This is standard quasi-Newton condition, right? And then our new quasi-Newton condition in this way by using this form. Or we can approximate the G in this form directly, and then our quasi-Newton direction condition in this form. So in summary, so the refinement matrices must satisfy the block quasi-Newton condition in this way. Right? Suppose we use for example, the BFGS method. Right? So in this way, but the computational cost is still huge because the size of variables are large. Therefore, we can combine the so-called sketching technique. Originally, we are using this U and V, right, with large matrices, but we can replace those two matrices by certain kinds of sketching matrices. And in this form, we can reduce the complexity. So let me show you some convergence analysis. Of course, we have to add some assumptions. First, the stochastic gradient is unbiased, and the variance of the stochastic gradient is bounded. And we assume the BK is positive semi-definite. Of course, this is a very strong assumption, but it holds in for example, in the quasi-Newton case. No, it's not exactly holds because we compensate the easy part by adding some quasi-Newton expression. Here is the global convergence. So under those assumptions, we can show the gradient convergence to 0 almost surely. And if the sample size increase sufficiently fast, then the sequence also converge superlinearly almost surely. This is some numerical results on autoencoder on simple data sets such as M-list and faces. So let's look at those lines, those curves. At the bottom, we can say that so SKQN means we use the easier part. We use the empirical Hessian matrix, and we have 3 variants of the quasi-Newton approximation. For those figures, we can say that our quasi-Newton method can be better than KFAC, also SGD at item. So this is our quasi-Newton method. So next I will show you a few methods based on the natural gradient direction. So remember, I will review the KFAC matrix. So let me. So yes, if you yeah. So you are right. So actually, on those simple data sets, or quasi-Newton method can also faster in terms of the computational time. But however, this kind of methods, all kinds of quasi-Newton methods so far, is not efficient on large data sets. For example, ImageNet. So not only our method, but I guess all other methods. So this is a big challenge. So I guess the reason is, for example, in TensorFlow or in PyTorch, certain kinds of operations are not supported well. So this is the reason why we develop another method based on the natural gradient direction. So as I already explained, okay, there's another question. Okay, thank you. So any question on the quasi-Newton part? So on small data sets, the quasi-Newton method works very beautiful. But on large data sets, it's very challenging. Okay, so if there are questions, we can also talk about it later. So as I mentioned, there's a KFAC approximation to the Hessian matrix, right? So this KFAC is approximated the inverse directly by using the structure of by using a Kroneck approximation to the Hessian matrix. So here we use we compute the inverse from another perspective. So let's look at the empirical confirmation matrix. This is the exploitation of one-to-one matrices, right? So again, in practice, we can only afford to compute it on a mini batch. For example, on a ordinary GPU, because the memory size, right? On GPU, the limit is the memory size. So because even because we have a large neural network, we have in those algorithms we have to store quite a few things. For example, the gradient, the parameters itself, and also the data sets. So even you have a Tesla with 100, the number of byte size on a single GPU is also very quite limited. For example, 64, or I guess it's quite limited, or a little bit larger. So the size of this mini byte actually is very small. Therefore, if we in practice we compute this empirical confirmation matrix, we compute a subexample version. For convenience of notation, we denote this gradient by UI, right? We take summation, and this size actually is very small. Therefore, this matrix, this subexample the empirical confirmation matrix is itself is a no-rank matrix. Of course, this is the UI is a combination of many layers, depends on what kind of neural network you have. But suppose we just take a look at one layer. Of course, if you have many layers, so similarly we only take a block diagonal approximation. Therefore, on each layer, the natural gradient direction can be computed in this form. So BK is the approximation. We take the empirical subexample of the empirical confirmation matrix, and this matrix is no rank, as I just explained. So if this matrix is no rank, then once again we can use the SM&W formula. The direction D can be written in this form. So G is the subexample of the gradient, and the U and the capital U is a connection of the gradient. If you take a look at this one, so U is all those gradient. So let us call this a gradient per example, and the G is a gradient, so the mini batch gradient, and this U is a capital U is a connection of gradient per example. So therefore, the natural gradient direction is a linear combination of the gradients. So essentially it's kind of gradient type method. But the B is defined in this way. But the size of this matrix is only the number of byte size. As I just explained, the byte size usually is quite small. But the main challenge is that we compute the B and also compute the U times B. So if in ordinary problems, there's no difficulty, right? It's a matrix times a vector B. There's no difficulty at all. But if you take a look at in neural networks, for example, in ImageNet, VisNet, then you have trouble. I will explain later. Because for example, let's look at the fully connected layer, the number of rows of U can be 10,000, more than 10,000. Then, right, so we have to compute U transpose U and the U transpose G. So this kind of computational cost can be expensive, because the number of rows is huge, but the number of columns is small. We have a K observation. B actually is a solution of a linear least square problem in this way. So therefore, we can do sketching once again. So we can multiply a random matrix before before this term, right? Before this term. For example, we can take a few hundred from U, a few hundred rows from U. Then the accuracy actually for fully connected names, the accuracy is very close to the original problem. But in this way, we can reduce the computational cost pretty much. Another thing is, but the main trouble is not the convolution name, because on a few names, for example, for VisNet 50, the number of parameters can be up to a few million. Then things can be complicated. Let's explain the reason. So let's take a look at the gradient. The gradient is a declaration of those two matrices. So the storage of the gradient itself can be expensive. So why? So let's count the dimension of G, I, and AI and the gradient. So this is the size of G, size of A, size of the gradient, right? So then you say on a few names, if you look at those names, so UI, the dimension of UI is much larger than the dimension of the G and AI. Right? So if we store the gradient is explicitly, then we have trouble because the dimension is huge. However, for on the fully connected name or a few on some other names can store the gradient explicitly is benefit. For example, in this case, because dimension is much smaller than the dimension of G and A. However, on those names, you see all of those names, so it's not affordable to store the UI explicitly. Therefore, the question is, can we only store GI and AI instead of the gradient? Then can we still perform compute the natural gradient direction? The answer is yes. We can also use the sketching. So essentially, we construct our sketching matrix in this way. So it's a quadratic product between two random matrices. Then you plug into this formula, right? And do the computation explicitly. We have computed three things. So U times U, U times G. This is Z. Okay, because then here those three things, right? Those three things, those two things are relatively simple, can be done by sketching. However, so those things, we have closed form solution where you only have to do sketching on small matrices, and then you can compute it quite easily. However, if you look at the multiplication of U times B, or we take just an arbitrary C. So this linear combination of UI, but now UI is not explicitly available. What we have is this form. We only have GI and AI. So once again, we use the similar idea as KFAC. So what is KFAC? KFAC is first take the expectation and then do the quadratic product. So similar things can be done here. First we do the average linear combination of G and AI, and then do the matrix multiplication, right? So if we do this naively in this way, we have the number of matrix multiplication is a batch size, and then the cost can be expensive because the size of G and AI can be quite different. However, if we do it in this way, right, first take an average and then compute the matrix multiplication, then the computational cost can be controlled. So we have convergent analysis. So similarly, the gradient stochastic gradient is unbiased, and the variance of the variance is bounded. we have a sketchy matrices. We assume those two assumptions are satisfied. Of course, those two assumptions are satisfied with high probability in certain cases. Therefore, once again we can prove a convergence of the gradient with high probability. Okay. So we can also establish linear convergence in wide neural networks. We can say the very simple case. The structures of function is defined in this way, and the loss function is L2 square, and we denote the Jacobi matrix by J, and the gradient is this way. So if we apply our sketch natural gradient method to this case, where U is transpose of Jacobi matrix, then the natural gradient direction dk is this matrix, where M K is instead of the Jacobi matrix times Jacobi matrix, we have another one. This matrix in the middle. This is one matrix. This only difference from the, for example, from the natural gradient method itself. Then by certain calculation, the dk can be computed in this way. Right? If the parameter lambda k converges to 0, then this dk is constructed in this way. So it's very similar to the neural tangent kernel for those things. Then therefore we can do the analysis, establish the linear convergence of the function values. Okay. So let me show you some simple numerical experiments on simple data set, for example, CFA 10, CFA 100, and SVHN on small neural networks. It's not small, actually. It's also have, for example, have 10 million number of waveforms. And on this neuron, on VGG, actually we can say our method is faster than SGD with momentum, also faster than ADAM. And the KFAC the performance of KFAC is not good because on this architecture, the size of matrix to invert is quite large. However, in our method, we never compute the inverse is explicitly, therefore our method is cheaper. And for SGD to achieve certain kind of accuracy, it failed in certain cases. Similarly, on WASNet, they have similar performance. So those kind of method, those kind of task is on some small on one GPU. Okay, and this comparison with the comparison of time. In terms of the on the WASNet, it's quite similar, but on the VGG, our method can be faster. So next, how about if we want to compute solve the problem on ImageNet? Because the size of data is huge, then we have to do parallel computation. So we designed a distributed natural gradient method. So we divide the data on different nodes. So we allocate the data on different nodes. So the goal is we're trying to reduce the communication cost. Hopefully everything is done parallel without data knock. So we have few strategies. So we can compute the direction on each node separately and then combine them together. Of course, for this parameter, this BK, right, we have to use a diagonal approximation, right? So because it's very difficult to send this U, broadcast this U among different nodes, because U is huge, right? U is huge. So we only do computation locally. Another one is if you do this way, so GK is a mini batch gradient, the summation of those things. Then you have to, if you take a look at this expression, you have to do 2 or reduce operations, so for separately, for each of those summations. So in order to reduce the communication cost, so instead of use GK here, you can use the GK minus 1. You can replace this GK by GK minus 1. Therefore, those 2 summations can be done all at once. We just need 1 or reduce operation. Another thing is we have to compute U times C, right? This is done implicitly. So for this GI, for each G, we first do average on each node, and then synchronize those data, and then approximate U times C in this way. Okay, this is what we do in our parallel computation. So let's check the parallel efficiency. So number of batch size is increased from 512 to 4,096. For those 3 cases, actually those GPUs are on 1 node. And if we want to use 32 GPUs, then we have to use 2 nodes. So there's a main difference, because for those cases, all communication is on a single node. Everything can be relatively very good. But in this case, we have to do a communication between 2 nodes. If the connection between the 2 nodes are not faster, then the computational efficiency can be small. So, however, for all cases, we tune our algorithm such that it can converge to achieve the 75.9 accuracy, testing accuracy in 41 epochs. And the total computational time is those numbers. So on 32 GPUs, we are able to do it in 50 minutes. And if we compute the scaling efficiency, so the formula in this way, this is the ratio between the batch size, and this is ratio between the computation time, right? So efficiency can be above 0.9. So I guess this is, of course, the efficiency is quite good. So we're going to compare our method with KFAC and SGD on VisNet, on ImageNet. Once again, we want to achieve a test accuracy of 75.9. The batch size is 256. We'll do it on 4 GPUs. So we can say this line corresponds to the SGD. So this is computational time. So SGD is the slowest algorithm. So this number corresponding to the updating frequency of the matrix U. So we do not update the matrix U at every iteration. So for example, this update at every 800 iterations. Similarly for KFAC. So our method is, so this variant is the fastest algorithm. And for this algorithm, if KFAC only updated the frequency matrix, computed the inverse, because it had to compute the inverse, right? at every 200 iterations, then we say the computation time is quite expensive. But however, if you compare this red line between those two lines, right? So our method is much faster. Overall, our method is around can be 40% faster than SGD. Okay, this is a training accuracy. This is my talk. Thank you very much for your attention.